we go. We have done these kinds of problems before. We spent whole chapters on these in Algebra 2. So we've got here our exponential growth or decay. So it depends on whether the amount is growing or getting smaller that we use the plus or the minus. For the R, we're using whatever rate of change we have, our percent, as a decimal. P, that's our principal. It's our initial starting population. It's very similar to when we had our A times B to the X. Our base is what we calculate with the rate. It's how it's growing, how it's changing. A being our starting amount, that initial population. A y-intercept. We use our t as our x. It's our amount of time. So if we're looking here at this problem for Albany, Kentucky, these kinds of problems are used all the time for population analysis. If we know that Albany, Kentucky is growing at a rate of 2% annually, and the current population is 25,000, how could I write an equation for this town? The amount of people in the town is going to be found by what? Our 25,000. That's our initial population. That's what we're starting with. So this guy is our principal. That's starting amount. And we're going to have our 1. And are we going to use the plus or are we going to use the minus? Plus. How do we know it's plus? It says growing. What are we going to add? Oh, yeah. Yes. So we're going to put our rate. We're going to put it as a decimal. 0.02. And then I'm going to slow down. I promise. I'm just going to put our power of t for right now. This would be a very generic equation for just this town. I could use this equation to make a prediction for its population for any number of years from now. Whether it's in 2 years, 5 years, 100 years, I could make a prediction. I could substitute in a number for t and get that value. I could simplify this a little bit. I could add together my numbers in the parentheses. That's totally fine. I could put it as 1.02. So we could simplify this a little bit. I'm just filling a little bit of time here to give you guys a little bit more time to write. 1.02 to the t. That is also another generic equation. So if I want to make a prediction for the population in 5 years, what are we going to do with that 5? Sub it in for t. Exactly right. So this would be our t. So we could put into the calculator that the amount of people in our town is our 25,000 times our 1.02 to the 5th. So how many people are going to be in this town? Yeah, we get 27,602. Did we get a decimal on it? Mm-hmm. Isn't it like 0.02 or something like that? Yeah. But we're talking about what? People. Can I put 0.2 of a people in a town? No. No, that's me taking a hand and lobbing it randomly into town square. I think it will affect the number of people who live there if I just start tossing random body parts in. So whenever we have living creatures, we are going to round to the nearest whole number. Do not tell me 0.2 or 0.02 of a person is there. 27,602 people. No matter what kind of living creature, no matter what our opinion is on that living creature, whether it is people or mosquitoes or spiders, no decimals on living creatures. I don't care if it's elephants or people or mosquitoes or spiders or rats or whatever creatures, snakes, they all count as whole figures. We'll round to the nearest. Yeah. We're making predictions. It's kind of an estimate, kind of a vibe anyway. So it's never going to be perfect, so we'll just round to the nearest. Questions on this first one? Sure. I told you, it just takes us longer to write them than it does to do the math on them. So we're going to do another one very much like it. We've got a new car, costs $23,000. Pretty affordable car right now. And its value decreases by 15% each year. So we want to find the car's value after just 3 years. This is a real thing that happens with cars, by the way.
Isn't it like the second you drive it off the lot, it starts decreasing?
Yep, by about 15%. Yes, dear.
Can we get another glue stick? This one's almost.
Oh, absolutely. I have vast quantities. Still not even into my brand new glue sticks for this school year. I think I only have 3 more old ones, but they're still hanging. All right. So let's get our kind of generic equation for this. What are we going to do? Our amount is our $23,000. That's our starting amount. That's the principal balance on our loan. That's how much it starts at, $23,000. Then we have our 1. Are we going to use plus or are we going to use minus? Minus, because it is decreasing. Our value is getting smaller. We have a positive value, and we are decreasing it, making it smaller. That's how we know it decreases. What is our R going to be? Our 15%. Ooh, that's not the highlighter. 15%. How do I write that for my equation? 0.15. Do not put 15 in there. If we want to have a generic, we put to the T. That would give us I could make a prediction for any possible number. I could make a prediction for 1 year, for 3 years, for 10 years, for 20 years. We could simplify this, and if we do that, we'll be able to see the fact that this is not going to be exponential growth because 1 minus 0.15 gives us 0.85. And when our base is smaller than 1, if it's between 0 and 1, that's when we're looking at exponential decay. If our base is bigger than 1, it's growth. If it's smaller than 1, it's decay. So that subtraction is what makes us decay here. So it's really important whether we use plus or minus. Very important. And if we want to make our prediction after 3 years, what are we going to do with that 3? Substitute it in for t. That's our unit of time. So we can have that the amount our car is worth, which started at $23,000, depreciating by 15% over 3 years. What is my car worth now? $14,000. Say it louder. 124. Any living creature, we round to the nearest whole number. Money, 2 decimal places. Round to the nearest. Okay. So we've done these before. It's been a long time, but we've done them before. We're going to do one that I just am going to give you an equation, and we're going to kind of find our pieces independently here for a second. So we're going to have one more before we go to the next story. Because I'm going to give you an equation. Our A equals 3,000 times 0.75 to the t. And it's just thinking about them in a slightly different manner. What is our principal, or our starting amount? And want to see if we can identify what rate of change we have. What's our percent? So if we look at the equation, 3,000 times 0.75 to the t, I want to find my principal, the p, and I want to find the r. So this is relative to our equation we were looking at A equals P1 plus or minus R to the T. So I want to find P and I want to find R. So what is our principal? 3,000. Is this number out in front? That's our principal. That's the starting amount. Okay, so we know our principal is that 3,000. What's our rate going to be? Yeah, I was going to say, it's coming out of this center piece here. We know that this is going to be a subtraction because it's less than 1. So we know that our rate is going to be set up as 1 minus R equals this bit here. 0.75. Because that 0.75 is smaller, we can set it up as a subtraction. And here we can solve for R. I can subtract 1 from both sides to get our minus R equals minus 0.25, which means our rate is 0.25. So as a percent, 25%. This has a decay of 25%. It is decaying. It is getting smaller. So more often than not, it is going to be us writing the equations given that information, but occasionally we are also asked to find the information given an equation. So if we can go both directions with it, we are in great shape. Questions about our kind of basic interest? Because there's another version.
Oh, God.
I mean, technically there's 2 more versions, but we're going to start with one more version where we're looking at our compounding interest, which is for the most part very similar. The only thing that's different in here is having this additional n, which is how many times per t are we doing the thing. So how many times per year are we compounding? The rest of the pieces all mean the same. We're still going to find our total amount with our principal. We use our rate as a decimal. We have our t as time. And it's just how many times it's compounded. So we've got here that Laura has a $4,800 savings account earning 4.5 interest. And we want to know how much money she has after 20 years compounded in these 2 ways, compounding semi-annually and compounding monthly. So let's start with the pieces we know. What is our principal? 4,800. So the amount in our account is going to be based off our 4,800. Are we going to use the plus or the minus? Plus, because she is earning interest. So her amount is going to grow. We are then going to have our fraction. What is our rate going to be? Ooh, that's still not the height. We need this guy as a decimal. So be really careful. It's not 0.45, 0.045. It moves 2 spots over, 0.045. When in doubt, we take percent per 100. So we go 10, 100, 2 decimal places. So 0.04. What's up? I couldn't hear the question. Divide by 100, yeah. 4.5 divided by 100. If you had an absolutely sure way to get there, it's where the name percent comes from. It's per century, per 100. And for this one, we're also told our time up here at this point of 20 years. So the only thing that's going to be different in these two equations that we're working with is this n piece. And what n is are these compounding words that we have down here. So we're going to divide our fraction by n, and we need to multiply our exponent by n. So when we're looking at compounding semi-annually, how many times is that going to be? 2. Semi is means splitting it in half. So semi-annually is not one of those things that's used super often, except for things like the Bath and Body Works semi-annual sale, like that kind of stuff. That just usually means twice a year. So we'll put this together as one big equation, 4,800 times our 1 plus our 0.045 over 2 to the power of 20 times 2. So we divide our rate by the n, and we multiply our exponent by the n. From here, we can type the sucker in the dang on calculator. Get an actual value. We can simplify this a little bit if you want to and put our 20 times 2 in as 40. Or we can put it in the calculator and hit that up exponent and just hit 20 times 2. As long as it stays in the exponent, you are golden. What are we going to get for the amount in her account after 20 years compounding semi-annually? And 91 cents, I do believe. Cool. Round to the nearest, 2 decimal places. I would say banks will do it whichever way is more beneficial for them. So if it's money they owe you, they'll truncate it. If it's money you owe them, they will round up. So they just kind of go round to the nearest, and we'll call it close enough. But corporations tend to go in whatever way favors them. So let's see what's different when we compound it monthly. So if we're compounding monthly, how many times are we compounding? What's our n going to be? 12. Because there are 12 months in a year. So what our n is going to be is how many of these are in our time, are in our years. There's 12 months in a year, so we're going to use 12. Other than that, the rest of the equation is exactly the same. So our amount is our 4,800. 1 plus 0.045 over 12 to the 20 times 12. Make sure you remember to switch the n and the exponent as well. The most common mistake I see on these is that we only switch out one of the n's. So we either forget to switch this guy or we forget to switch this guy. That's the most common mistake I see on these compound interest problems, is that we only switch one n. So just be really careful, especially when we're working at 2 equations with the same situation. Forgot. You do not have to put like the commas and stuff in money, like totally fine. It's just sometimes easier to read. They're reading her sign today. This is not good to me.
I mean, that's good, but at the same time.
Well, it's so good. So good. We're good. It stops the people from coming later going, what I not?
Yeah.
And then they just stare in the window and it looks all creepy, like, Schmerp. These are the problems we're working with on niche.
So what?
The one Laura, or the one after Laura. Laura's here now. Okay, questions on Laura and her situation? We're gonna do one more like this. So we're gonna look at Aaron here. Hey, Aaron. Who has spent $5,200 on his credit card that charges him interest. And so we're looking at how much money he's going to owe. We have a couple of ways we can look at this one. We're going to be real careful with some signs. All right. How are we going to start this one? What are we going to start with? What is our principal? 5,200. It's the amount we start with of his debt. It's how much he owes. Then we're going to have our 1. Are we going to use a plus or are we going to use a minus?
Minus.
To say he owes him $5,200 and he's being charged interest, is he going to owe more or is he going to owe less?
Less. Wait, I'm so confused now.
I was going to say, because he needs to pay them back this money, right? They're going to charge him interest because he owes them money. Does he owe them more?
Yes.
It's like a fee. So the amount he owes is going to get bigger. So it is a plus on this one. If you want this to be a minus because it's charging him, you would need to pay attention to the fact that he owes $5,200. So if you want to do that he charges and use a minus, we would need to have a negative here. What that's going to do would make it reflect over that x-axis, and we'd still wind up with a growth equation. So you can set it up either way. If you want to do that he charges and use a minus rate, we need to pay attention that he owes the $5,200 and have it be negative $5,200. If we set it up as he needs to pay this $5,200, that is the amount we're owing, we add the interest because he owes more. So that's one of the reasons I have this one in here, is because they love to play those games of owing and charging interest, so the double negatives still make it be growth. What is our rate on here? What is our R? 0.21. For this first one here, compounded weekly, what is our N?
52.
52. There are 52 weeks in a year. We have our 52. 52 in our exponent. And what's our T? 3 years. So a lot of the pieces are going to be very much the same between the two equations. The only thing that's going to change is our N. So compounding weekly, how much does he owe his credit card company? $9,751.20. Then we're going to compound this quarterly. It's going to be very much the same. All the pieces are the same except for our n. 1 plus our fraction. Yep. I'm just copying over the things that don't change. For this last one, like here, we're compounding quarterly. What's that going to be? What's our n going to be for that? 4. Whenever we see quarter, think how many quarters are in a dollar? There's 4 of them. Or how many quarters are in a school year? Oh, snap. Same thing, 4. Or if I quarter something, I'm cutting it in fourths. So our n is going to be 4. The rest of the equation stays the same. The only thing that's changing is that 4. How much will Aaron owe if his interest is compounded quarterly? Say it again. 9,608. There we go. And 79 cents. Yep. Schmear. The more times it's being compounded, the more it's going to change. The fewer times it's compounded, the less it will change. So if we're comparing different kinds of compounding, quarterly will be smaller than weekly. Daily will have if it's a growth, have a higher value than if it's being compounded semi-annually. The more times it's being compounded, the more it will change, up to a point. There's only so many times I can subdivide it. I could compound it weekly, I could compound it daily, I could compound it hourly, I could compound it minutely, I could compound it secondly, I could go millisecondly, but we kind of reached this limit on how far it can go, and that is where one of those really random numbers that exists in math is born from. As we continue compounding closer and closer and closer and closer together, there was a limit that was found out as kind of the maximum closeness that you can get compounding. And that's where we get E from. You do not have to memorize E. I don't have E memorized to any sense of decimal other than it's 2.7-ish. That's about as far as I go on decimal places. It's not like with pi where there's competitions for how many decimals of pi you know.
I love how pi is more famous.
Pi is significantly more famous than E. Euler's number. It's 2.718 blah blah blah. If you ever want to see it, we're going to put E in the calculator, put an exponent of 1, and ta-da, you can see it. We don't need to be able to generate it or pull it back up manually ourselves. The only time we're ever going to need numerical answers for E, we will put it in a calculator. The way we use this is when we're looking at these compound interests, there's one other kind of compounding, and that's instead of, dividing it by quarters or months or weeks or days or years or whatever, we use E, and that's when we get that per equation. P is still the same thing. It's still our principal. R is still our rate as a decimal. T is still our unit of time. The one thing we're going to have to do that's a little bit different is if we have a rate that is decreasing, we're going to need to put that as a sign on our rate. So if it is decaying, we're going to have a minus on the rate. If it is growing, we're going to keep it positive. So we're going to have to figure out growth or decay and put that as a sign on our R. Other than that, the values are the same. E is a number. It's a button on the calculator. And just to be specific, I have one on me right now. It is, you'll hit the green button and then ln. And that'll give you E. It'll even kick you up into the exponent. So E is a number. We're not substituting anything in for E. It's kind of like pi. So our first E equation that we're going to use here is this next one that talks about Amy. Excuse me. There you go. So when Amy was born, her grandparents put $5,000 into a savings account that earned 4.6% interest, being compounded continuously. And we want to know the balance it's going to be when she graduates at 18. So,
The needle point.
what's up?
I said needle point right when you said so.
Oh, yes. Yes. Indeed it is. What is our principal for this situation? 5,000. That's still going to be our P right here. So we're still going to start this out that same way with our 5,000. Then we're going to put E. E is a number. It's a button on the calculator. We're going to use a button. Is this going to grow or is this going to decay? Grow. They put money in. It's a savings account. We expect this balance to get higher. They're giving us interest. They're paying us to hold on to our money so they can use it for other stuff. So what is our rate? 0.046. So we're going to have 0.046. And what's our T? 18. Boop. 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 Times 18. So when we go to put that in the calculator, you can type it in just like that. I gotta grab my calculator and I'll pop it up here for a second just to help us see. Oh, teeny tiny calculator. Let's make that better. Okay. So again, just as a reminder to put that in the calculator, we would put in our, helps if I push the buttons that are right. There we go. 5,000. To get E, hit the green button. Then we hit ln. It shows you the E and it kicks you up into the exponent. And then we can just straight up type in our rate, our 0.046, just making sure it's looking at the right one, times 18. You can type it in just like that. Like you don't have to simplify it. You can, absolutely valid, but you can just type it in like that.
So, 443.60.
Mm-hmm. Yep. So she would have in her account, with her grandparents putting that 11,000 in, the amount she has is that 11,443 and 68 cents. Which is why they always say when you start saving for college or retirement, the earlier you start saving, the easier it's going to be, because they say $5,000 and it more than double. The earlier you start saving, the better things work out.
And the more you start saving, the more you put in.
The more you put in, the more you put in early, the way faster it's going to grow. Okay. So before we do any more of those story problems, I want us to look at when we're trying to do any solving stuff with E. It works the exact same way as when we were solving before with different bases. It works very, very similar, but I want us to practice that solving again. These will be our last two for the day. We'll do those last two stories on Monday, and we'll finish it out on Monday. So we're going to take a look at this one. This one is looking a little gross for this left-hand side. We've got e to the 4th to the x times e to the x squared equals e to the 12th. So we need to do a bit of simplifying here, because I can't just compare my exponents when I have different pieces. I need to get the exact same base, one base, to be able to compare my exponents. So I need to be able to smush together this left-hand side. What can I do with e to the 4th to the power of x? They multiply together. So this is the same thing as having e to the 4x times e to the x squared equals e to the 12th. When we are multiplying bases, bless you, if we multiply bases, what can I do to the exponents? Add them. So I can smush these guys together to make one singular base if we add those exponents together. So this is the same thing as if I had e to the x squared plus 4x equaling e to the 12th. Once we have it here, we can go, those e's don't make a dang on difference anymore. Once I have the bases the same, the bases are irrelevant. I just care about when my exponents equal each other. So no matter if it has e's or not, all I need is my bases to be the same. And then I don't have to look at that base anymore. When our bases are the same and we have 1, all I need to do is compare my two exponents. So we're going to take our x squared plus 4x and find when that equals 12. How do I solve that one? Subtract 12 on both sides. Because we have a quadratic, we need that sucker to equal 0 before we can solve it. Plus 4x minus 12 equals 0. What can we do from there? Factor. Pair of numbers that multiplies to make negative 12. Adds to make 4. Positive 6. Negative 2. That gives us our factored form of x plus 6 and x minus 2. Which means what are our solutions? Negative 6 and positive 2. Which are both valid options for where these x's are. I could substitute in a negative 6 here as an exponent, or here as an exponent. I could substitute in 2 here or 2 here. Totally valid. And if I did that, they would wind up at exactly the same value. Absolutely. Okay? So we are going to stop there because we have like a minute to the bell. We are not going to do the quiz on Monday either. We're going to do the quiz on Tuesday just because we're not there yet. Yeah, we'll do the other equation on Monday. We will finish this out. We'll finish the last 2 stories, and we have the reason we're pushing this test is because we still have to do some graphing. We haven't done the graphing yet. So quiz 9 will be on Tuesday. If you are interested and you want to have it now, I do have a review for quiz 9. I will put it out on the table. It does include the graphing stuff that we haven't talked about yet. We'll talk about it on Monday. I have them over here. No, homework will not be due Monday. It'll be due Tuesday as well, just because It has graphing on it. Yeah, we can talk about the graphic. Moving it out of 18. And you don't have to do the review. The review is entirely optional. It's just, I have had feedback that we like the reviews, we want the reviews. I make them, you can have them. You don't have to do them. Woo-hoo.